Hello, everyone. I'm Norman Wildberger. Thanks for joining me on this adventure. We're looking at classical to quantum mechanics, physics, foundations of that subject, and we're carrying on with Albert Einstein's incredibly important paper on the electrodynamics of moving bodies. Today, what I want to do is I want to critique or think a little bit about this first section called the kinematical part, definition of simultaneity, which I read for you a little while ago, and it only has 2 pages, okay? And I want to examine this with a view of, what does it mean? What's he trying to say here? And are we comfortable with the notions and the way they are presented? So maybe I shouldn't have to reiterate the great respect and admiration that I share with pretty well everybody for Albert Einstein and his courageous and insightful and just remarkable achievements in the direction of both relativity and quantum mechanics. But I also don't want to be afraid of pointing out ambiguities or perhaps logical difficulties or at least gaps, where they exist. I think there's something to be gained from that. If we have a healthy respect, but also not be unwilling to tackle difficulties, even if they're historically kind of entrenched. So let's have a look at this, all right, shall we? And we'll start from the beginning, and we're going to read it. Again, I'm just going to go over the main issues where I think there's some questions arising. So let us take a system of coordinates in which the equations of Newtonian mechanics hold good. So already here with this very initial sentence, there's all kinds of questions or, issues that are being raised here. And Newtonian mechanics classically is considered to be in a rather fixed framework where we have a fixed notion of space and time. It might be useful in this context to think of a 2-dimensional space, so maybe given with x and y coordinates, and a time coordinate t. So a Newtonian framework for that would be basically a 3-dimensional linear space, perhaps Euclidean space involving also a metrical structure, okay? But in such a space, every point is uniquely associated with a triple of numbers x, y, and z, which are the x, y, and t coordinates of that position. So that is, I guess, our first guess as to what he's saying here, that we're going to take such a system of coordinates. But there is a question. There's a question of whether he's introducing a model for our world, saying, well, here's a mathematical setup in which we're going to investigate some notions from physics, or whether he's saying, let's take the space, the world that we are living in, and impose on it such a coordinate system and examine the space that we're in it in the light or in the mental context of such a Newtonian coordinate system. Okay. So if a material point is at rest relatively to this system of coordinates, its position can be defined relatively thereto by the employment of rigid standards of measurement and the methods of Euclidean geometry, and can be expressed in Cartesian coordinates. So he is assuming a Euclidean structure. But in the next paragraph, we see that this Euclidean structure doesn't really extend in his mind to time. So if we wish to describe the motion of a material point, we give the values of its coordinate as functions of the time. Now, crucially, we must bear carefully in mind that a mathematical description of this kind has no physical meaning unless we are quite clear as to what we understand by time. Now, strictly speaking, Newton might object to this, that Newton might say, well, we are just assuming a 3-dimensional structure in which one of the coordinates is time. So there's no question about what time is. It's just the third coordinate in this 2-dimensional space together with a 1-dimensional time. Okay, so, but I think what this makes clear is that Einstein is thinking about space as having a system of coordinates. So we have a system of coordinates on space, but not necessarily also for time. So whether this is actually really a Newtonian system or not is a question. Okay. Okay, so, but I think it's quite reasonable to say, we need to investigate what we understand by time. Even if we are working in some kind of mathematical framework, when we want to apply it to the physical world, we have to make some kind of correspondence. We have to say, well, what in the physical actual world actually corresponds to this mathematical idealization of a time axis. So we have to take into account that all our judgments in which time plays a part are always judgments of simultaneous events. And in a Newtonian system, you might say that corresponds to the idea that if you specify a t-coordinate in this three-dimensional space-time that we're considering here, then that defines a plane, okay, and then that plane then consists of all the points whose time coordinate is that given one. So yes, and those are all considered simultaneous. But Newton would say, yeah, but we don't need to say anything extra about that. That's not really saying anything more than saying, well, when we specify an x-coordinate, we're talking about also a plane in a different kind of direction, which consists of all the points in this space-time whose x-coordinate is the given one. Okay, so then he talks about simultaneous events. For example, the time of something is really a statement about it corresponding to, position on your watch or your clock, and we're noting a simultaneity between an event and the position of the clock hands. So it might appear possible to overcome all the difficulties attending the definition of time by substituting the position of the small hand of my watch for time. Okay. And in fact, such a definition is satisfactory when we are concerned with defining a time exclusively for the place where the watch is located, where this notion of simultaneity is, well, it's maybe sort of self-evident, especially if we're thinking about making observations with light, which goes so fast that we can't register how fast it's taken for the light to come from the watch to the eye or from the eye to the observed event. But it is no longer satisfactory when we have to connect in time series of events occurring at different places, or what comes to the same thing, to evaluate the times of events occurring at places remote from the watch. So I think he really is thinking about having coordinates on the space, like on the two-dimensional space, say, in the example I talked about earlier, and then thinking about, well, how do we actually establish a consistent notion of time from this? Now, okay, in this next paragraph, we might, of course, content ourselves with time values determined by an observer stationed together with the watch at the origin of the coordinates, and coordinating the corresponding positions of the hands with light signals given out by every event to be timed and reaching him through empty space. So he's sort of positing an observer, in quotes perhaps, together with his watch. And strictly speaking, probably we should put watch in quotes too, right? Because, what is a watch exactly? I mean, are we assuming that we already have a sophisticated physical structure like this? Let me remind you that historically, clocks have been hugely problematic things to construct accurately. The notion of a clock or an accurate clock that actually registers, not events like days and years, but actually, minutes and seconds even. That's relatively recent. It's only a couple of centuries old. Okay, the technology inside this Seiko watch is remarkable and difficult to understand and appreciate. Okay, so we should not think about this thing here as some kind of elementary God-given physical aspect of the world. This is actually a highly structured, complicated device. And I think we should be suitably nervous about pinning our understanding of fundamental physical reality on a prior abundance of such technical devices. Doesn't ring true to me. Okay, anyway, so what's he meaning here? Well, he's saying that we might be able to get away with just having a single observer stationed with a watch at the origin and looking at things with light signals given out by every event to be timed and reaching him through empty space. So if something event is happening there, then there's a light signal that coming from that event and reaches him through empty space. But this coordination has the disadvantage that it's not independent of the standpoint of the observer with a watch or clock, as we know from experience. I'm not entirely sure exactly what he's saying here. I mean, there is the issue of if I get a light signal from some remote event, okay, maybe I can register that, but how do I know where and when that light signal started? All right, I mean, I do have to go over there and look at the coordinates of that point, and or get somebody else to register when that that light signal sort of emerged. So we arrive at a much more practical determination along the following line of thought. Okay, so he's now maybe getting around some of the ambiguity here by trying to pin down more clearly what he means by sort of time in this semi-Newtonian setup. Okay, so have a look at this line. If at the point A of space there is a clock, an observer at A can determine the time values of events in the immediate proximity of A by finding the positions of the hands which are simultaneous with these events. Okay, I do have to flag that, he's talking about a point A of space. And I suppose by that he means a point A in this Newtonian mathematical model of space. If Galileo was around, Galileo would say, yeah, but he can't be talking about real space, because in real space, the notion of a point is hugely problematic. Why? Well, because it depends on your motion, right? If I go like this and I say, well, consider this point here, this is point A, and this here is point B. Well, that only makes sense if you're sort of viewing it in a frame with me in which we're both kind of stationary, or where we both appear to be stationary, crucially, okay? But in fact, certainly we are moving dramatically through the world because of the rotation of the Earth and the orbiting of the Earth around the sun, which Galileo would have been well aware of, okay? So Galileo would have said, yeah, but it just looks like this is defining a point. It's not really. It would be like me saying, hey guys, consider this point A here. See, the end of my finger, that's the point A. And let's introduce the second point. This is the point B. Right? You might think, well, wait a minute. You're not defining points in space because those things are moving. Well, that's exactly the same problem that we have even in a more simple-minded fashion by just thinking that, we can define a point in space independent of the obvious motion of all these systems in which we're parts of. While we're getting philosophical, I also have to say a little bit of, at some point we're going to have to talk about this notion of an observer. And especially with quantum mechanics, this becomes a crucial, crucial topic, which we'll have to say much. But even at this point here, we should probably flag, okay, that there's this implicit assumption here that we can make sense of having an observer, that the observer is somehow independent of these things and can objectively make measurements and deductions and apply theories and so on. That's a huge assumption. Okay, it very well might be that an observer, say like this one here, is actually a biological creature, which is itself controlled by laws of biology and chemistry, which ultimately depend on laws of physics. And that, any notion of self-determination and free will that this observer thinks that they have is simply a consequence of their thought processes not being sufficiently large scale and clear. Okay, so it might actually be that this observer is just a part of the phenomena, just as much as spaceships or clocks or balls being thrown up in the air. Okay, so that's a topic we'll have to return to. Very interesting questions of free will, which also hugely important in talking about quantum mechanics. But let's just flag that there's an issue there. Okay, so let's give Einstein the benefit of the doubt here and suppose that, he's thinking perhaps more of a mathematical model for space rather than space itself. So we have this mathematical model in which space coordinates are given in a Newtonian fashion, but time coordinates are not. Okay, and then what he's saying is that if we have 2 points A and B in this space, okay, that makes sense perhaps in that context, then an observer near A can determine a sort of a local time by looking at things close to A and having a watch. And an observer at B could also do the same thing, assuming that the clock at A and the clock at B are in all respects resembling each other. Now there's another huge assumption which plays a big role in special relativity. This assumption that we can create frames, reference frames, perhaps far apart, with essentially identical clocks. So maybe I can get my Swiss or Japanese factory to churn out lots of identical watches. But if I want to, send copies of these watches to Neptune or to Alpha Centauri or to Andromeda, I have to accelerate them. I may have to do a lot of acceleration and decelerations, and it may take a lot of time. And are the clocks, as a result of that, still the same in all respects as the ones that we started out with? That's a very big assumption, probably realistically unwarranted. But in fact, what he's proposing here is, in fact, even though he's not saying it, is a way of actually getting around that problem. So then we get this crucial little section here. We have so far defined only an A time and a B time. We have not defined a common time for A and B. For the latter cannot be defined at all unless we establish by definition that the time required by light to travel from A to B, time in quotes, equals the time, again in quotes, it requires to travel from B to A. Now, he's right to put those times in quotes, and we should flag that use of time is different from the A time story and the B time story separately. To posit that there's also a notion of time from an event over here in A to a time over here in B is already some kind of additional assumption. But what does that mean? Okay, so he's trying to get at that now by saying, well, let a ray of light start at the A time, T sub A, from A towards B, and let it at the B time be reflected. So it's reflecting light off of B from A and recording when it gets back. So it starts at time T sub A, and it gets back at T sub A prime. Okay, and he's saying then we can use this reflection property of light to synchronize the two clocks, to guarantee that they have sort of a common time by this equation here, which I've pointed out is really equivalent to saying that the B time coordinate of the light hitting it and being reflected is the average of the initial and final times read at A. So that's a definition of when these two clocks at A and B are synchronized. And I think this is a very important idea that we can use light signals to somehow, make sure that we're talking about something that's sort of consistent. Now, this consistency he addresses, and he does it in a way that's not that comfortable for a mathematician. Okay, so he says we assume that this definition of synchronism is free from contradictions and possible for any number of points, and that the following relations are universally valid. And then he says a few things in terms of sort of a symmetry of this notion of synchronization and a kind of a transitivity. At this point, as a mathematician, I would prefer to say, well, look, you're working in a mathematical model, okay? So you're actually free to make these definitions in the mathematical model, and then you could actually aspire to verifying that these things are true. In other words, you make the corresponding definitions in this mathematical model, and then you check, you compute, you create theorems that say that this notion of synchronization, which is like a relation, is actually satisfying this reflexive and transitive property. Okay, that's the kind of thing that a mathematician would want to do. Okay, but he's not a mathematician, fine. But anyway, so that's just something to think about. And then in the last part of it, thus with the help of certain imaginary physical experiments, we have settled what it is to be understood by synchronous stationary clocks located at different places, okay, and have evidently obtained a definition of simultaneous or synchronous and of time, which Newton would maybe say, well, yeah, okay, so that's just another way of establishing what I would just have assumed automatically, that we have this linear system ultimately, which is three-dimensional, which includes time as a coordinate. But you're able to get at the time coordinates sort of from a local position by using the path of light. So then he says further, in agreement with experience, we further assume the quantity 2ab over t prime a minus ta equals c to be a universal constant, the velocity of light in empty space. Okay, this is very big sense here. So this is essentially the second postulate of special relativity, that that this velocity of light in empty space is a well-defined concept. Now, you see, I'm nervous here because what he's doing, he's introducing light, okay, which is very much a physical thing that we don't have a good mathematical theory for. Maybe somewhat better nowadays than in his time, but light was a complicated thing. It had this electromagnetic aspect. They thought it was waves. They thought it required an ether, like waves typically do, some kind of underlying medium in which to propagate. Okay, but how do we build that into this mathematical model that we started out with, right? He wasn't saying, well, let's consider the physical world. He was saying, let's consider a mathematical model of the physical world. So now if he really wants to introduce light into this mathematical model, he would be better perhaps to say, well, let's assume that certain lines in this affine space or Euclidean space that we've posited have certain properties, a certain parallelism or a certain slope condition that's universal. Okay, so that it's more of a something that's built into the mathematical side. But what he's doing here is he's now going back to the real world and saying that actually in the real world, according to Michelson and Morley and electromagnetism theory at that time, that the velocity of light appears to be the same in empty space. So he's making some concept about the world. But as soon as he does that, okay, as soon as he leaves the Newtonian framework, then Galileo steps up and says, wait a minute. If you're working in the real world, okay, not some idealized mathematical model, then in the real world, the notion of velocity, I'm sorry, is not a well-defined one, at least not unless you spend a lot of time thinking about it. Because of a velocity of anything, it doesn't make sense, right? In a Galilean system, if I ask the question, what is the velocity of this eraser? That is a nonsensical question because it obviously depends on the observer. And if we want to compare the velocities obtained by different observers, say, of this eraser, then that means we have to have a prior way of synchronizing the unit systems in those two observers. This Klingon warship might not be using meters and seconds. It's using something entirely different. Okay, so to say that we're getting the same velocity of light requires a prior consistency of units across the board. And then we're exactly in that same kind of position that he was worrying about before, about how to establish the similarity or the synchronization of clocks, not to speak of the synchronization of lengths, which are implicit here in this AB, which is supposed to be a distance. Or actually probably a displacement from A to B. So, there's lots of brilliant stuff here. He's thinking about things in a novel way. He's moving away from entirely a Newtonian point of view, even though he's sort of adopting it. But where he's actually sitting and what the real meanings of a lot of these words that he's using is not at all really very clear. And finally, it is essential to have time defined by means of stationary clocks in the stationary system, and the time now defined being appropriate to the stationary system, we call it the time of the stationary system. Okay, so there's a distinguished system in which things are fixed, which is the time of the stationary system. But overall, I honestly, if I was an editor of a mathematics journal, say in 1905, and somebody had submitted this to me, to be completely honest, okay, I don't know if I would accept it. I would say, there's interesting ideas here, but you have to expand considerably on what you're saying, and you have to clarify much more clearly the meaning of the terms that you're using, and whether you're actually talking about the physics of space or some mathematical model of it. And if you are talking about a mathematical model of it, then you need to spell out more clearly what exactly that is and what the underlying geometry that you're assuming is. Okay. But it's still brilliant stuff, for sure, right? But there's questions here, and these are important questions to think about.